I'm glad to do today's presentation. At the study, I will introduce myself. My name is Wei Song Hong. I'm from a graduate industry of the applied science and the technology, Taiwan Tech and R&D Center. And today's topic is about the mechanism of the self-assembling of the smart electrical response graphene-based membranes. I remember this class is called, it's just the introduction of the engineering, is it right? So I think we can talking widely, talking widely because it's just the introduction of the engineering. So we can talking anything about this topic. Today I will introduce about a membrane, and this membrane will be includes the material graphene. Graphene material is very popular recent year, and we're also talking about electrical response property for these membranes. So the first slide I will talking about my research topic. The beginning of the study I focused by using the positron. Okay, the I think you never heard about a positron ionization technology to determine the free variance on the thin film composite membranes. Then I moved to I from the Zhongyuan University, moved to the Taiwan Tech. Then I focused my topic, changed my topic to the preparation and application of the 2D material based graphene, 2D material graphene based membranes. In addition to the paper preparation, we also focus on the industry cooperation facing to wide range of the application graphene as membranes with many cooperation with the university or in the industry, for example, like the NUS and the OSFOR and the Thai Power and the Formosa and or TSMC. This kind of the very famous industry, and we also got many awards from it from these studies. Then we also introduced the according to the report of the World Economic Forum, is pointing out the effect of the weather problems. The people facing the challenge of the safe drinking water, and it is the issue we must pay attention to. Then we can also see the global. Here is show the global top 5 challenge each year. The water problem is always on the list. We can see, and in the 2050, the water problem is the top 1 in the challenge. Then the problem of the water and the energy is inseparable. We want to obtain the drinking water from the ocean, but the traditional reverse osmosis or desalination requires a lot of the energy. So how to get a more energy efficiency drinking water? The development of the new generation membrane material is the important issue. So in this slide, we discuss the basic reverse osmosis membranes. What is the structure of the composite membranes? We know the dense membrane. Okay, it's generally membrane. The structure is like the dense membrane then provide the highest selectivity, but flux is lower because of the greater resistance. This structure is called asymmetric membranes. The asymmetric membranes provide a high flux but cannot maintain the selectivity. So if we use this membrane to separation for the seawater desalination, the permeance sign is also has a lot of the source. So then we combine the advantage of these two kinds of membranes and fabricate the composite membranes. The top part is the composition is the selective sand layer. The bottom part is the porous substrate. in general, this time we're also talking about in generally the membrane can be organic or inorganic. The organic membranes are flexible, cheap, and easy to make the modules, but they are poor thermal and chemical resistant, and also the short membrane lifetime. From the inorganic membrane, that has a good thermal and the chemical resistance, and also a longer membrane lifetime. But the problem of the inorganic membrane is brittle, difficult to make a module, and high price. So we combine both advantage organic and inorganic membranes to prepare the graphene based membrane. They can have the both advantage and for the further applications. Okay, so in this slide we are talking what is the graphene. Okay, the graphene has become to the popular material. The amount of the graphene research includes a lot, particularly after the two Russian researchers attained the Nobel Prize in the 2010. Its advantage includes the very thin, about 3.5 angstrom, good molecular strength, high transparency, and high flexibility, and they also has a higher thermal and electrical conductivity. Here I also has a show video to I will show to you to easily to understand what is the graphene material.
Ever been bothered by an ultra-slow download? How about a phone that won't stay charged, or a cracked touchscreen? Imagine you were stranded on an island with nothing to drink. What if science came up with a way to solve all these problems with a single chemical compound that you can find 1,000 gigabytes in 1 second? A smartphone fully charged in 5, super thin, flexible, and unbreakable touchscreens, and a personal salt water filter. All this and more is possible with the Nobel Prize-winning material. Personal salt water.
So here is also show the graphene-based membrane has the high potential for further membrane application on the seawater desalination. There will be rejected the salt in the feed, and only the water can pass through the graphene layer.
All this and more is possible with the Nobel Prize-winning material graphene. As early as the 1940s, theoretical studies predicted graphene to have high levels of electrical conductivity, thermal conductivity, and breakage strength. Graphene was also known to compose the subunits of the common material graphite found in a pencil. Draw a line, and groups of graphene flakes slide onto.
So when we was young, when we was a student, we used a pen to draw line of the line. On this line, we can find a single or few layers of the graphene on it.
Producing a mark. The problem was that no one could figure out how to isolate a single flake. Scientists tried various chemical means, resulting in nothing more than graphitic sludge. Mechanical polishing got them to 1,000th of a millimeter of graphite, but that was still about 1,000 layers of graphene. In 2002, a group from the University of Manchester took a more MacGyverist approach. Using their self-dubbed Scotch tape method, physicists Sir Andre Geim and Sir Konstantin Novoselov peeled away at a graphite crystal, producing flakes that became vanishingly thin. An atomic force microscope revealed their success. The elusive material finally in hand, scientists were able to see just what graphene could do. As predicted, it's an excellent electrical conductor. The free electron on each carbon atom of graphene enables movement of charge across the surface. Moreover, its thermal conductivity, or ability to transfer heat, is higher than that of copper.
Yeah, this is very important. So for the single layer of the graphene sheet, their thermal conductivity is better than the cobalt, even the silver. The conductivity is better for this kind of the ion material. So their basic properties is really good.
Transfer heat is higher than that of copper. Mechanically, the strong bonds between carbon atoms and the inherent stability of an hexagonal array combine to produce the strongest material known to man. Nonetheless, the bonds of graphene retain remarkable flexibility. As a sprayable two-dimensional surface, it can be used to easily tune the properties of other compounds. A lot of people are excited about graphene's possible versatile applications. Because graphene has very high conductivity and is almost completely transparent, it could be used to make more efficient electronics. These electronics have the potential to be more environmentally safe once graphene extraction techniques are improved. With its high breakage strength, graphene could be the key to lighter and stronger building materials. New techniques for creating nanoscale pores in sheets of graphene indicate that it could be used to make ultra-thin filters. As scientists think of new ways to use this supermaterial, it's worth recalling its humble entry into the scientific world. Using a piece of Scotch tape and blocks of pencil lead, two scientists were able to make a groundbreaking discovery. In 2010, the Royal Swedish Academy of Sciences awarded Gaiman and Vasilev the Nobel Prize in Physics for their efforts. Together, they proved that scientific innovation does not always require fancy instrumentation. It requires persistence and creativity.
Okay, so yeah, so it's very fantastic. It's really impressive material. Okay, so now we can know the graphene just easily can get from the tape set peel up from the graphite. Then we can give the single layer of the graphene, and those researchers, one is all of my good friends in Rome's labs. They got the Nobel Prize in the 2010. Then here, this slide will also show the most common derivative of the graphite. Okay, here we can show the derivative of the graphite as the follow: graphene oxide, and the reduced graphene oxide. Each has its own characteristic. The graphene has the complete carbon cycling structure, so it has the good conductivity, but it's hydrophobic. The graphene oxide, okay, so researchers consider how to dispersion the graphene in the water or in the organic solvent. So the chemical-based researcher, they consider, okay, we make the oxidation functional group on the graphene sheet. So we can see many oxidation functional groups, for example, like the hydroxy, capacity, and epoxide group. Those groups improve the hydrophilicity, so graphene oxide can dispersion in water easily, but it's not conductive. Then the researcher consider how to recover the graphene property. So they make the reduced graphene, prepare the reduced graphene by the heat or the chemical methyl to prepare reduced graphene oxide. It can recover the sun conductivity, but based on the surface defect, their conductivity only can recover maybe 70% or 60%, cannot return to the original. These slides show the graphene-based membrane has many applications. They are waste solvent recovering and the wastewater treatment, carbon dioxide capture, power generation, package engineering, and the other application. So it's point out the graphene oxide membrane is the wide range using in the many field. And the key idea of in this research is the article in the Science published in the 2012. This article used the freestanding graphene oxide that allow the water molecule quickly to pass through block the alcohol molecule. But those members is still not stronger for the application, because we can see this membrane, the mechanical stress is really is poor. So how to improve the membrane performance, we will consider in the future. This slide also show the graphene oxide is like the molecular safe, and that has the stronger potential for the oil water separation. They also point out the water will be quickly pass through in the graphene oxide layer, and they can inhibit the salt penetration by some cross-linking or some the functional group attention. Then the membrane performance will be increased. In our lab, lab, we also consider how to improve the graphene technology. So we focus, the first important is we focus how to dispersion the graphene in the water. From the photo, we can see if we add the graphene in the water, they will be separate, because the graphene is a hydrophobic. That is the hydrophobic material. So when we add it in the water, they will be on the water. But if we add it in the organic solvent, they will be dissipated on the bottom of the solution. Then we consider how to dispersion the graphene in the water-based solutions. Then after the dispersion, then we can prepare the membrane from the lab scale to the pyro scale. So roll to roll casting is also important. And after the casting, the graphene membrane also can has a good conductivity. Then based on our lab, we also consider how to prepare a different structure of the graphene layer. We can prepare the graphene layer that has the highly ordered laminar structure or random structure. Both has their own application. From the separation or designation, the highly ordered structure is good. But from the random structure, maybe they can have the super capacity and some battery application. So in this slide, we also show, okay, based on our graphene membrane technique, we got so many awards from the world. Okay. Here is show the graphene membrane for the EMI shielding and the heat distribution. So we can see when we add the graphene in the membranes, their heat distribution rate is increased a lot. And for the EMI shielding, when we add we can see the blue lights. When the graphene adding, the EMI shielding property will be all increased. Here is also show we can prepare based on the graphene membrane to prepare the graphene sponge structure, and this graphene inker is also easily to casting on the paper or on the wood, and to form a good conductive graphene layer. And from the Oxford University, they also help us to announce our technique in their website to show the graphene in our lab, the graphene membrane, not just in the lab scale. We also can scale up by roll-to-roll casting, and they can easily for the industry application. So this slide also show from our lab we can prepare the any kind of a structure of the graphene. We can prepare the highly laminar structure of the composite membranes, highly porous structure, and each kind of the structure for for the graphene application. We also point out where graphene membrane is cooperation with the industry to the ESMC, the Taijidian, and we help them to recover from their process. We will help them to recover the isopropanol, and it is the available solvent to reuse in their production. So we know the advance in the industry improves the world livelihood. However, those developments also lead to a lot of the environmental pollution. The semiconductor and the electronic industry usually use a lot of the alcohol as the solvent during the production and for the cleaning process. Therefore, the important issue is how to collect and recover the waste solvents. So this slide is show the alcohol is widely used in the chemical industry. There are good solvent, cleaning agent, raw material, chemical intermediate, and the renewable bioenergy. And how can alcohol be separate from the water? Generally, the membrane is a good the membrane separation is a good solution. So this one is talking about our by using the preparation, follow the solution diffusion models. The feed solvent will be first dissolved on the membrane, and the diffuse in the membrane. Finally, they will be dissolved at the other end of the membrane. So, and we also prepare the graphene oxide from our safe by the commercial harmless method. We can get a graphene oxide from the graphite, okay, based on the chemical reaction. Then we can prepare the graphene oxide. Then we use this graphene oxide to prepare the self-assembling method to prepare the membranes. And we also can cross-linking because the graphene has the many oxidation functional group. So we can, based on the chemical, add some cross-linker to prepare the graphene oxide framework membranes. So first, we will discuss the different methods to prepare. Okay, we can check the uniformity of the different methods to prepare the graphene oxide membranes, and the effect of those membranes on the graphene layer structure and on the dehydration of the butanol. The three different types of the self-assembly method are using pressure, vacuum, and the evaporation as the driving force to prepare the membrane. For the pressure-assisted method, we can see the graphene oxide layer has a more homogeneous surface. From the cross-section, okay, from the cross-section, we can find that the graphene oxide layer is dense and thin. And if we compare it with to the evaporation method, the membrane surface cover is waste. The graphene layer is the rose. Graphene layer is the structure is the rose and the thick. From the TM result, okay, TM is really tiny scale to determine the graphene oxide layer. We can find that the pressure-assisted method, the graphene structure consider a highly ordered laminar structure. The result is because the pressure does not change. Okay, the pressure does not change during the assembling process. Hence, the graphene oxide layer arrangement is highly ordered structure. For the evaporation method, we find that the graphene oxide layer has a lot of the loop. It's because the evaporation method induce the upward driving force. So the graphene oxide, the graphene edge of the graphene oxide, they will be circularized together to form the the circle structure. So this structure, we can find the structure is loose and thick. So for the data of the membrane performance of the butanol water, we find that the graphene oxide membrane prepared through by the pressure assisted method has the high permeation flux and the high water concentration. Even at a high feed temperature, the water concentration still can maintain higher than the 99%. In the second part, we're talking about isopropanol separation. So here, based on the first topic, here we identify the characteristic of the graphene oxide there. From the SRD below, show that the graphene D space is about 8.5 angstrom, and the graphite D space is 3.4. It is because the graphene oxide, around the graphene oxide there has the many oxidation functional group, so it's the wider the D spacing. And the AFN below also show that the graphene oxide thickness is very thin, just about 1 nanometers. Then with deposition, the different amount of the graphene oxide on the membranes. So here we use the SM to obtain the variation in the amount of graphene deposition there. When the graphene deposition amount increase 10 times, the thickness is grow from the 100 to the 1,000 nanometer, and the membrane turn from the membrane surface image. We can see the membrane turn from the yellow to the black, and even based on the deposition amount increase, the graphene membrane also has a good flexibility. And here in this slide, we also discuss the effect of the different graphene oxide deposition amounts on the membranes. It was found that the graphene oxide composite membrane show the excellent separation efficiency. The water concentration is higher than the 99%, and the flux is reached to the 2,000. Then we find the really interesting phenomenon. When the graphene oxide deposition amount is increased by 10 times, the flux is almost unchanged, suggesting no resistance to the permeation. So we can see the thickness increased 10 times, the permeation rate only reduced only the 7.9%. It's really interesting because when the thickness increase, generally the resistance will be increased. But here, based on the graphene property, the resistance only the permeation rate and the resistance only reduce 8% in this type of membranes. And at a high temperature, when we increase the temperature from 30 to 70 degrees Celsius, we also can maintain the water permeation in permeation at 99%, and the flux increase from the 2,000 to the 4,000. It's because the high interaction between the graphene oxide layers, so there's stronger pipe interaction can maintain the membrane stability. We also compare the membrane performance, follow the graphene membrane, chitosan Teflon membranes, and the polyamide membranes, and the commercial sources membranes. We can find the permeation flux, the graphene-based membrane that has the higher permeation flux, and this kind of membrane, also, the graphene-based membrane also can maintain the water concentration in permeates. So here we also mention about the graphene, what the graphene oxide membrane can maintain the high flux. So we use the AFN to check the hydrophilicity. We for the adhesion test, the AFN hydrophobics. We use the silicon nitride as the tip. We find that the greater repulsion around the graphene arsenide edge. So it is a point out that the graphene arsenide edge is hydrophilic. So based on this hydrophilics, the water can quickly to absorb on the graphene arsenide layer, and the center part is hydrophobic. So water will be quickly pass through in the center part. So it is why when the graphene arsenide layer, the deposition layer increase, the water permeation, the resistance is not increased a lot. Okay, it's also the point out the graphene highly dynamic structure, and the piece of the graphene, the edge is hydrophilic, the center is hydrophobic. So the water molecule will be quickly absorbed in the edge, and also pass through from the graphene arsenide layer. Then we consider after the butanol and the isopropanol separation, we will consider to the ethanoldehyde separation for ethanol water separation. So this line from our original experimental designs, we expected the graphene arsenide membrane can use in the separation of the ethanol and the methanol, but it was not so. With ethanol as the feed, the water concentration is only 78%. With the methanol as the feed, the water concentration is 22%. So we consider how to improve the membrane performance. We can see the isopropanol butanol, the water concentration permeance is good, but for the methanol and the ethanol, the water concentration permeance sign is poor. It's because the butanol and isopropanol, the kinetic diameter is compared with the water, their kinetic diameter is huge. So those two is easily to separate. But for the methanol and the ethanol, their kinetic diameter is smaller. Similar, it's smaller than the butanol and the isopropanol. So when we separate it from water, it's difficult. Then we consider the graphene arsenide has the many oxidation functional group based on our introduction. So we do the cross-linking of the different diamine monomer with the graphene arsenide oxidation functional group by concentration reaction. So we prepare the graphene arsenide framework structures with the variation graphene D species, and it will be used for the separation of the ethanol. So here is the structure show when we use the diamine to cross linking with the graphene arsenide from IR spectra, it's easily to get a amine functional group. And from the cross-section SN image, when we fix the graphene deposition amount, we obtain the increasing the thickness of the graphene arsenide framework there. Okay, the thickness increase. This result may be due to the different chain lengths of the diamine monomer into the graphene arsenide layer. The result seen in different thickness. So this slide is really important. Here we point out when the unmodified graphene arsenide layer, when we immerse the graphene arsenide in the water molecule will be penetrated between the graphene arsenide layer, and the graphene arsenide, the thickness, there will be swell, and the D-spacing will be increased. After cross-linking the graphene arsenide framework membrane, the change in the D-spacing at a dry and wet state is not clear. It's because after cross-linking, the framework structure will be will be inhibit the swelling effect in the wet state. Then here we discuss the performance and to separation the 98% ethanol in the water using the graphene framework membranes. So the unmodified graphene oxide membranes, water concentration in permeance is only 78%. For the graphene oxide framework membranes, the water concentration is higher, particularly if we use the EDA as the cross-linker, the water concentration can reach to the 99%, and the water permeance is the 113 permeation flux. When the temperature increase to the 80 degrees Celsius, the water concentration also can maintain at 99%, and the flux increase to the higher than the 2000. The solid square is pointing out the commercial membranes. We can see their flux and their permeation, the water concentration in permeance, both is poorer than the graphene oxide membranes. Finally, we point out that for the methanol water separation. Here is also interesting. We see the graphene oxide membrane is the good dispersion in the water, and we consider in the methanol separation from our lab, the original consider is using the next study, the graphene oxide framework for methanol separation, but the performance is also not good. It's because the huge of the graphene oxide sheet, if we just use the tiny cross-linker to link each other, link the two sheets, their sheet stability is also not strong enough. So here we consider is use the polymer, the chitosan as one of the hydrophilic polymer. We use the polymer. We try to use the chitosan to cross-linking the graphene oxide sheet, and we're looking forward they can has the good stability for the methanol separation. But we can see the graphene has a good dispersion in the water, but when we blend graphene with the chitosan, we will form the membrane with uneven surface. It's because we never consider the charge between each others. The graphene oxide is negative charge, and the chitosan is with a positive charge. So when we blend each others, there will be formed a stronger ion complex between that. So finally the membrane, the solution is complex. So when we testing this membrane, we got a really ugly membrane. To solve these problems, so we prepare the reduced graphene oxide membranes. The reduced graphene oxide membrane, we can see the reduced graphene oxide membrane, the solution in the water, their dispersion is decreased. But the interesting is that after blending the RGO, the reduced graphene oxide, with the chitosan, their testing solution become well dispersion, and based on it, we can prepare the uniform membrane for the methanol dehydration. So it shows the membrane can easily to based on the reduced graphene oxide, the chitosan, we can prepare the uniform membrane, and also can easily to scale up to the row to row scales. So the graphene chitosan membrane structure is due to the negative charge of the graphene and the positive charge of the chitin. So blending between the graphene and the chitin will be formed a stronger ion complex, and the real thing is the aggregation. After the graphene reduced to the reduction, the weak electron negative of the reduced graphene oxide inhibited the ion complex, the formation. Then this is what we can prepare a uniform and highly laminate graphene, highly laminate structure of the graphene, the reduced graphene oxide membranes. Based on the well dispersion, and we can get the good reduced graphene oxide membrane for the methanol separations. After all of the alcohol dehydration, then we challenge it to the difficult separation membranes, the acetic acid dehydration. Okay, so here is the acetic acid separation is also the big challenge in the industry. Is so we prepare the graphene based on the graphene chitin, the experience. We use the graphene and the PVDF to prepare the membranes, and then has the nickel structure, and this structure is stable for the acetic acid separations. After it, we also focus on prepare the ultra thin graphene oxide membrane for the forward osmosis membrane applications. You have quickly to show to you. Then we also consider if on the previous study we all use the graphene oxide for the different kind of the separation application. Then we also consider how to directly use the graphene for the separation. We know the graphene cannot be dispersed in the water. So in this study, we try to use the graphene oxide, induce the dispersion of the graphene in the water. It's because the graphene oxide and the graphene layer structure is similar. Okay, so when we dispersion first, we dispersion the graphene oxide in the water first, and then we add the graphene in it. Then we can prepare the well dispersion solution. And this one is good for the membrane preparation of the graphene oxide and the graphene membranes, and it's also good for the nanofiltration applications. Here we also introduce the opportunity potential of the concentration dehumidification by using the graphene oxide membranes. The idea of the dehumidification is use the low temperature condensed water. The commercial method is using a compressor to provide a low temperature by doing the heat exchange. So the dehumidification is generally the high energy consumption by the compressor. So how to reduce the energy consumption of the dehumidification process? Lesson here, the membrane technology maybe is a good option. So here is the Professor Tsai from the Singapore National Singapore University, their mechanical department. He pointed out that the membrane dehumidification can reduce the energy consumption by 40% compared with a commercial compressor. The membrane dehumidification does not need to using the chemical regeneration, such as the chloroform fluorine material for the cooling, the cooling down the water. Therefore, it is the more environmental friendly. Therefore, it is the improves the development of the high efficiency deformation membranes. In our lab, we also prepare the graphene oxide membrane by using the different methods to prepare the graphene oxide membranes, and we can find it the SRD define the effect of the different humidify on the layer despacing. Because if during the deformation, if the membrane it make a stronger swirling effect, the water and the gas both pass through. So for the deformation membranes, we want to the membrane only water pass through, but the gas cannot be passed through. So close linking the membrane is the way to solve these problems. By using the close linking the graphene oxide to form the framework structure, and there will be inhibit the swirling effect. Okay, so it is the performance. Okay, I don't spend much time on it. Here is the point out. Compare with the previous literature, or compare with the compressed method for the dehumidification. Our study has a good selectivity and the water vapor permeability. And this technique, we also got the R&D award, the top 100 awards next year. Then I will talking about the smart membranes, smart polymetric membranes. We know the response membrane is a hot research topic in the recent year. This is a review article from the Professor Chu group. Is teaching the Sichuan University. They facing the challenge of the environmental pollution. The membrane must be upgraded to the smart and the more response. The control of by control the chemical structure to obtain the response membrane, we can prepare many kind of the response membrane by thermal, pH, ion response, mathematical line, and the glucose and the molecular and the magnetic method to prepare each kind of the response membranes. So in our lab, we also based on the polynippon, we synthesize the polynippon to prepare the thermal response membranes. So this one we can see, okay, when we by the polynippon is the one of the thermal response membranes. So when we close it between the graphene oxide layer, then by tuning the different temperature, we can find the shrinking and the swinging of the polynippon material. They will be create a different morphology of the graphene oxide there. So we can control the response structure of the graphene sheet. On the photo, we can find is really interesting. Okay, at a low temperature, A is at a low temperature, B is at a high temperature. We find that the graphene dispersion is clear in a low is really clear well dispersion in a low temperature. However, when we increase the temperature, the membrane will become turbulent. Okay, they will become aggregation at a high temperature. So at a high temperature, they will become the color will become dark, and some condition there will be aggregation at a high temperature. It is because the switchable phenomena can be also obtained in the microscope. Okay, here is also show their response property at a low temperature and the high temperature. We can see at the low temperature, their nanoparticle is small, and at a high temperature, each kind of the membranes, their chain aggregation, so the particle will be increased. Okay, and we also show the good response between that. So finally, we will obtain the feed temperature on the preparation performance. So during the membrane performance test by at a different temperature, we can find there. We also can tune in the different performance. So we also report the permeability of the graphene membranes response mechanism. The response that has the different type of the response, the whole cross linking, whole graph, and also the polymer and the framework response. So compare with many response meso, those kind of response meso, we find the electrical response is the phase response in our study. So here is showing out the piezoelectric property. Okay, based on the time limitation, I don't spend much time to explain it. Here is show the conventional here using when the piezoelectric property always uses the PVDF membranes, but the commercial PVDF membrane their criticality is the alpha phase. This kind of the structure, the membrane is no piezo is the anti-piezoelectric property. It's only if we can change the beta phase to the alpha phase to the beta phase. The beta phase structure is like it. Okay, the foreigner group is in the one side and the hydrogen group is in the other side. This kind of structure we call it the beta phase, and this structure can has the good piezoelectric property. So the commercial method to change the PVDF structure to alpha to the beta, we can using is the electron spinning, thermal heating treatment, or high voltage to induce the alpha phase to the beta phase, or electron spinning meso, or some heat treatment. We can this kind of the treatment can prepare the piezoelectric property, piezoelectric membranes. But in our study, we just missing the graphene in the PVDF, and the graphene can self-induce the PVDF arranged to the beta phase structures. So based on this electron response property, the graphene PVDF membranes, we use it in the alcohol dehydration. When we provide the charge to the membranes, the PVDF part will be swell. Okay, the PVDF part will be swell. So when the change the charge is it can return to the original. So we can control the interface channel between the different voltage, different charge. When we turn on the voltage, the PVDF part will be swell. When we turn off the charge, the membrane will be returned to the original. So the interface channel will be changed, and it's good for the any kind of feed solution or feed pollution separation. And here, based on the same idea, we also consider the membrane for the gas the gas separation by control the different charge, tuning the graph, the gas separation performance is good for the carbon dioxide, nitrogen, carbon dioxide, oxygen, and the oxygen nitrogen separation. Then the first two slides we provide the charge to control the membrane performance. Here by using the solar evaporation to produce the water and the produce the water and the energy at the same time. The ocean vapor, the solar evaporation can produce the water, and the ocean vapor can is good to the power generation. And the membrane structure, we also can see, the membrane structure after the graphene attended, the membrane also can have a good flexibility. And from the IR camera, we can see when we load in the graphene on it, the heat can protect on the surface. It's helpful for the water vapor and the water correction. And when we collect the water, check this water correction from the vapor, we check their water quality. We can see after the desalination, the water quality is good than the WHO standard. Okay, so this water can be directly to the drinking water. And then the next slide we're talking about is the water correction. Here, based on the same membrane, by using the shaking tank to produce the different hertz of the wave. Okay, prepare different hertz of the wave from the different hertz. Then we can find the waver can produce the energy. The result is show that the output voltage increase with the increasing the hertz. Then we find the optimal output voltage is at 1 hertz. After in the turbulent wave lead to the unstable output voltage. So the stable wave can create the good output voltage from this kind of membranes. Then finally, we also set up the power storage module to provide the graphene membrane can produce the water and the power generation at the same time. So you can see at the time increase the wave to the electric power generation increase, and we also can create the water from this module. Okay, finally I use this video as the final slide. This show the vapor power generation video. So when the shaking tank provides the vapor and the graphene membrane, we can based on the video to see is the power generation. The output voltage is shown on the square. Okay, here is clearly see from each waver, and the output voltage is like it. Here is showing 1 hertz. Okay. Okay, so based on this membrane is supposed to water collection and the power generation at the same time. Okay, so it's all of my report today. So thank you for your attention. And if the student has any question, okay, I will really welcome to answer it. Thank you. So I will say sorry to you because I also has the other meeting now. So if the student after my report, if you interested or find some question want to contact me, maybe you can based on the putting link to contact me and just write down, mail me, or just write down your question to me, and I will try to answer your question. It's okay. So if not further question, I think we will cancel the meeting now. Thank you.
Oh, thank you.
那今天就到这边了，好不好？
好，
好，谢谢，拜拜。
拜拜。